Because I was looking at Amazon yesterday and there were like a few, so I was confused.
I'll make sure of that and send a message after class today.
Right.
Okay, so as I'm sure some of you just heard, there was a question as to the addition of the book to Get. And truth be told, I don't know the official answer to that, although this edition that I'm using is supposedly from 1991. But apparently there's a 92 version. So this is what I'm going to do. I'm just going to say, I'll send a message after class. I'll resolve this and send you a message after class today. So, I don't know the answer to that. Okay. Additionally, I reviewed all the answers to the survey and decided, I sent an announcement, hopefully you saw that, as to when office hours will be. Right? So I think this fits with the most schedules that were reported. We'll have office hours on Wednesday, 4:30 to 6 p.m. and also on Thursday, 10 a.m. to 11:30 a.m. Okay? And this is good because, I don't know if you've noticed, but all our exams are on Thursdays. So I bet more people will want to have office hours right before the exams. Okay, so hopefully this will be helpful in that regard. So, good. Now, as promised, the beginning of most classes will start with the review of the homework assignments from the previous class. Okay, so let's just open it up and see if anybody has any particular questions about the homework assignments. We can go over anything in particular. I have some points I know I want to hit that illustrate important concepts, but your questions are most important. So I want to hear if there's anybody that wants to see anything explicitly that was assigned from yesterday. And if not, that's okay. But then I'll just go through some of the problems that I think are important to see. Greek letter rho, I believe. You mean by that, right? Is that right, Ziming? Yeah? Okay. Greek letter rho from question 1. Right. Okay. So question 1 asks, so this is part of 1.1, is rho of x comma y, which is defined by the cube root of x comma e to the y, a transformation. Right, question 1 asked you to take a look at all these mappings that are defined by these nice equations and determine whether or not they're transformations. So, good. This is, after all, what you were interested in. Yes, Zimi? Yeah, okay, great. So, does anybody have any thoughts on this? How do we address this problem? But first of all, in a broad sense, what must we verify to conclude that a mapping is a transformation?
It has to be onto and into one.
Yes. Thank you, me, Zach and Jordan both said that. We have to check that it's both onto and one-to-one. Okay, so given that, what do we think about this mapping rho?
E to the y doesn't map it everywhere.
Okay, good. So this is determining whether a mapping is a transformation. You're going to use all the essential knowledge you have about elementary functions that define those mappings, right? And what is the domain of the second component function? I'm sorry, the range of the second component function.
Negatives.
Positives, right?
Yeah.
E to the y is never
Yeah, well,
zero.
as I'm looking, yeah.
Yeah. Yeah. Yeah. So, okay. How do we, just a quick translation here into the language that we've used so far in defining these things. How do we show that this is not onto? So, how do you show?
We have to take a number, like a negative, and then show that when we try to invert the function, it's undefined.
Yeah, right. Or in other words, the easiest way to show the negative of a statement is to provide a counterexample, right? So if we come up with a point in the plane that has no corresponding point xy, such that this equation produces it, then we know it's not onto. Okay, so our broad intuition is rho is not onto. Because, well, what's an example of a point in the plane that never gets hit by this transformation?
One negative one?
Yeah, 1, -1, we had 0, -1. Anything with a -1 in the second argument will not get hit by this transformation rho. Because, for example, 0, -1 has no point x comma y, so that rho of x comma y is equal to 0, -1. Of course, such a point would have to have x be equal to 0, but there's no y satisfying e to the y is equal to -1. So rho is not a transformation. Okay, so let me just say about these early problems, it's a little bit difficult to say something that's entirely systematic about how to solve them, right? It kind of relies on your knowledge of elementary functions and applying the definitions that we built yesterday. What it means to be onto and what it means to be one-to-one. Okay? So, forgive me if that's vexing. Oh. Anirudh, are you trying to chime in?
I was just trying to, I misunderstood Thomas's point. I thought he was saying that 1, 0 is the, I just misread what he was saying. So anyway, but I also have a separate question.
Okay, great.
But yeah, so just a general question, like maybe kind of stupid, but like, how do you prove that something's like not a collineation? Like, for example, like x cubed, y cubed, like the first example in 1.1.
Mhm.
Like obviously it's a cubic and it's not a line, but how do you like say that mathematically?
So again, great question. But again, the easiest way to show something is not true, especially in these not very systematic problems, is to come up with some counterexample. Now, okay, so why don't we just talk about 1.2 for alpha. So 1.2 asks you which of the transformations from 1.1, the ones that we identified were transformations, are in fact collineations. Okay, so let's just write this down. 1.2. So in 1.1, we showed separately, we didn't do this just now, we showed that alpha of x comma y, a mapping defined by x cubed, y cubed, is a transformation, right? And just quickly, why is this?
It's right to utility.
Yeah, right. So, this is, we had an example very similar to this yesterday, right? So let me just write quickly, since u to the 1/3 power, comma v to the 1/3 power is the unique point mapped to u comma v for any numbers u and v, right? Yeah, okay, so that's pretty much, we did this example yesterday, although now our first component is cubed as well. No problem. Now, how do we determine if this is a collineation? Well,
Example equation for a line.
yeah, so what you want to do is take the arbitrary equation for a line, a capital X plus b capital Y plus c is equal to 0, and see what the image of that is under this transformation. Okay, so is alpha a collineation? Well, to do that, look at the image of the general line. Ax plus by plus c equal to 0. Okay, so what do we get when we essentially plug in our formulae for u and v in terms of x and y into these capital X and Y's? Yeah, okay, so this implies what we're really looking at is we look at the equation ax cubed plus by cubed plus c is equal to 0, right? And, okay, so we're essentially done at this point. But if you want to be slightly more rigorous, let's solve for y and look at the shape of that, the graph of that thing.
Right, and it also will show us what could be counterexample too, right?
Yeah, exactly. We can then pick specific A, B, and C's to provide a counterexample. Okay? So, solving for y, we get, obviously I've run out of space here. Okay. Y is equal to negative the cubed root of ax cubed plus c all over b. Right? Okay, so you can, not every choice of A, B, and C is a counterexample. Right? You can make a choice of A, B, and C to make this a line.
Notably, a non-zero C is pretty helpful.
A non-zero C is very helpful in producing a counterexample. Right? If we let A be equal to 1, B be equal to 1, and C be equal to 0, we just get the line y equals x. Right? So, let me note that. Not all choices of A, B, and C provide any counterexample. But most do, especially when C is non-zero, right? Okay. But, right, when C is non-zero, we see the resulting equation is non-linear. E.g., why don't we just I wrote something down here because I drew the graph of it, just so you can see what this kind of looks like. Okay, so here's the example that I happen to use. Let A equal to 1, equal to B, something very simple, and C equal to negative 1. Then what do you get? Well, you know, it's pretty close to linear. It's kind of like a line with a lump in it. It's roughly something like this. Still not linear though. Okay, so again, because we're in this initial phase, I recognize that it's kind of hard it's hard to tell what is completely rigorous. But even getting this far and saying that when C is not equal to 0, we definitely have something that's nonlinear, that's enough. Okay? Do you have something to say?
I'm just thinking about when A is 0, but it's still fine.
Yeah, right, but even...
It's nice to make all non-zero numbers here, but...
Right. Yeah. So I feel like, I feel like your question was really like, what do we have to say? And I just want to emphasize that, especially in this initial phase of the course, we're not, like for chapter 1, we're not fully formal and rigorous yet. So it's okay to just get somewhere here. That's a complete answer. But I mean, I hope that it will become apparent what is required as we move further in the course in terms of justification. And we will become fully rigorous over time. This is just the gentle entree into the whole subject. Okay? Good. So, what else should we discuss? Any questions before I just talk about some things I think are important about the homework? So then let me just ask you quickly some things I think are somewhat important. Really screws me up that there's no tray here. Keep having to go back to the table. Okay, so let me quickly ask you, how about in question 1.1, is beta given by cosine of x sine of y a transformation? Just really quickly, because, okay, so I'm seeing some head shakes. The answer is no, because the only reason I bring this up is because we should always remember the basic facts about all our elementary functions, right? I'm glad that we got e to the y, the domain of e, the range of e to the y.
This isn't inductive or surjective.
Right, fails both ways. This is neither one-to-one nor onto, right? No, since it fails to be both one-to-one and onto. Okay, good. This just follows from elementary properties of the functions that we all know and love, right? The range of cosine is just from 1 to -1. Likewise for sine, right? So any point that has either the x or y component outside the range 1 to -1 is not hit by this transformation. Right? Okay, now think about why it fails to be 1-to-1. Think about that. Okay, so how about this? What about another one from 1.1? Epsilon. Given by negative x and x plus 3. Is this a transformation? Okay, I heard a couple no's, and Jordan went a step further and said it's not onto. Right?
I was going 1-to-1.
This actually parameterizes a line in the plane. Both components are independent of y. Right? Okay, so you can graph this in the plane. This is just a line. I mean, again, you're right, it's both not 1-to-1 and not onto. But, you know, I think this example is useful to think of because it has a geometric interpretation. This is just a parameterization of the line, a line. Okay? So at 0, 0, we go up to 3. Sorry, to 3. Okay? And what happens at the point 1, 0? We go to -1, 4. Okay? And then it turns out this is the image of epsilon. It's just this line. Every vertical line
Is it projection?
in the plane goes to a single point on this line. Okay? So that is to say, in the domain of epsilon, every point on this blue line gets compressed into this point on my black line. And likewise for every vertical line. Okay? Oh, I actually said this wrong. Every point on this blue line gets compressed to this point, right? Because I went negative. Sorry. So yeah, I don't want to clutter this image, but this whole blue line gets compressed to here. Right? Because I have this negative x. Okay? So I think, yeah. Yes, thank you, Dal. I didn't see your comment, but you're right in correcting me. Okay. Okay. Good. So let's just do one more problem from the homework exercises. And of course, those are all fair game to ask about during office hours. If you have further questions, that's fine. But let's jump ahead to exercise 1.4, part D, which asks you, let me copy from the book so I don't screw it up. Find the image of the line with equation y equals 5x plus 7. Then you're told this is a collineation. Under the collineation, alpha of x comma y is equal to 2y minus x, comma x minus 2. Okay, so we kind of went through, I'm sorry. So Ryan asked, so is that onto but not 1-to-1? So, yeah, just to go back, Ryan asked a question about epsilon here. So why is this not 1-to-1?
Because all the points on that vertical line are the same output, well, the same image.
Exactly. So this blue line in the domain, which is the plane, the domain of epsilon, all those points produce the same point, and maybe I should put this in blue, if people on Zoom can even see that. All those points go to that blue point. All the points on this line go to this blue point. So that means there's more than one point in the domain that goes to the same point in the target. That's why it's not 1-to-1. Oh, I'm sorry, I misread your question, Ryan. So it's not onto because everything outside this black line is not hit by the transformation, by the mapping.
When the codomain has to be the plane.
Right. And the codomain, the target of a mapping, has to be the entire plane. Okay? So it's neither 1-to-1 nor onto. It's not 1-to-1 because this blue line gets taken to this single point. A bunch of points get taken to a single point. And it's not onto because the entire image of epsilon is just this line. You don't hit the entire plane. Right. Yeah. Good. Okay. So, we did an example similar to this 1.4 part D in class yesterday. So what's my first step here?
Find U and V, or
Say that one more time.
find U and V to show, like what you would normally go about showing its transformation.
Right. So technically what we're doing is assuming that there's some point x comma y that lies on this line. And then we want to express those x and y's in terms of u and v, the outputs of our collineation. Okay? So in other words, take x comma y on the line right, and then all we do is and set just what we have here as the definition of our collineation to u and v, right? U is equal to 2y minus x, right? X, and v is equal to x minus 2. Yeah, okay, so this of course implies we solve this equation only has one variable that we're concerned with. We want to put these in terms of x and y, right? So we'll solve this for x, just to get x is equal to v plus 2. And then plugging that in to here, we get u is equal to 2y minus v plus 2. Okay, so of course this just gives us that y. Okay, I'm going to skip all this algebra, right? If I want to solve this for y, what do I get? I get u plus v plus 2, all divided by 2. Okay? And then I just plug these expressions for x and y into the equation of my line. Okay? So I get u plus v plus 2 divided by 2 is equal to 5 times v plus 2 plus 7. Okay, and at this point, all you have to do is get your equation in the shape of where u's and v's replace x's and y's. Okay, you want to put it in the standard form of any linear equation. That is, ax plus by plus c equals 0. But here now you're letting v equal x and, I'm sorry, u equal x and v equal y. So Jordan asks, do I mean uv on the line instead of xy? So I'm taking xy on this line and then looking at the image of x and y under alpha, and then deriving an expression for the line that alpha takes this line to. Okay? Is that okay? Okay, good. Good.
When you write the answer for that one, do you want us to use u and v as our bound variables?
So, that's also a great question. Personally, I think I would accept that, but, you know, really, I should, because we're kind of taking variable names to be capital.
Right.
Okay, so let's just, I'll write a few more steps here, just to clear up any ambiguity. Okay, so if we do the algebra here and get this in the form of a standard linear equation, what do we get? We get u minus 9v minus 32 is equal to 0. I just did that by distributing 5 multiplying both sides by 2, combining u and v terms, and combining the constant term. Okay? So really the final answer is the image of y equals 5x plus 7 under the collineation alpha is x minus 32y, I'm sorry, 9y, jeez, 9y minus 32 is equal to 0. Okay, that's so cosmetic. Personally, I don't think I would take points off for that. But this is technically correct. Because remember, we're assuming that uv is some point that satisfies that equation. So to really give the equation for a line, we should go back to variables.
And the same variables.
You could use different variables if you want, but the purpose of this distinction between upper and lower case for points on a line and the equation that specifies a line is that you can reuse them, so you don't run out of letters if you have to do a bunch of stuff. Is that okay? Does that make sense with everyone? Okay? Okay, good. I think that's all those are the main subtleties of any point I wanted to make about the homework. Yeah. Okay, so maybe let's move on to chapter 2. Is that okay with everyone? Okay. Also, I know some of you have been in class with me before, but for those of you who haven't, I'm extremely error prone, especially when making computations on the board. Please correct me often. You know, I take the opposite offense to that. I greatly appreciate that, because I don't want to confuse anybody. Okay? Okay, so we've discussed the basic definitions about what a transformation is, and a particular type of transformation that we'll be interested in to study Euclidean geometry, namely collineations. So now we want to impose some additional structure on the types of transformations that we'll be studying. And this is where, remember yesterday I said that this course is intended to be preparatory to study group theory. So don't be intimidated by the use of the word group here. We're going to go through what it means to come up with a group of transformations, and it turns out that's the general, broad definition of what it means to be a group. Okay, and we'll say a little bit about that after we talk about what it means to be a group of transformations. Okay, but never fear, this is the primary example that we'll be working with all the first half of summer. It's just groups of transformations. And that hopefully will build your intuition for how to deal with arbitrary groups. So we'll just say a little bit about that at the end of this section. Okay? Or chapter, I should say, which will be tomorrow. Okay. So, right. Here's the definition. The identity transformation obviously it's a transformation. Which we denote iota. This is a lowercase curly I without a dot, another lowercase Greek letter. I'll just remind you, this is called iota, defined by, see, I'm going to have to make myself not put that dot on. I of p, iota of p, is just equal to p for all points p in R squared in the Cartesian plane. Okay, in some sense, the most boring or trivial of all transformations. Obviously, who can verify for me that this is a collineation?
A line's a line.
A line remains a line. If you don't move any of the points in a line, they remain on the same line. Okay, so the identity transformation is so boring that it's really nice. Okay? So, this is part one of this definition. Part two, if a set, which will denote cursive G of transformations, contains iota, it looks like a C, iota, then we say G has the identity property. Okay, so
So what is that?
this
The symbol, yeah.
this is a cursive G. It's a cursive capital G. Okay, yeah, so, yeah, I didn't give you a complete list of all the
Letters
notations.
that made up my existence when signing.
I'm sorry?
I have to sign a letter all the time.
Okay.
Terrible.
Yeah, so I didn't give you a complete list of notation yesterday, but for collections of transformations, we'll often use capital cursive Roman letters. There's just so many different things to keep track of that we have to use everything at our disposal. I'm sorry if that's confusing, but hopefully it will become clear with context. And you're gonna have to see this sooner or later. Okay. So, okay. For those of you who are already a little familiar with group theory, I bet you can see where this is going. This capital G, this cursive G, is the thing that we're going to endow with the structure of a group. And this is the first property of the structure of a group. Again, if you haven't seen group theory, that's okay. So Thomas asked, how strict is the nomenclature? When I'm grading your work, if you make it clear what you're saying and writing, I don't care what symbols you use. It doesn't matter.
Point everything.
Yeah, the point of me introducing this notation is because it's widespread. It's kind of like a piece of mathematical culture. So, it'll be easier for you to read other things, but in your own work, you can label things whatever you want. Don't overload symbols. Don't use them twice for the same thing. But as long as you clearly label what you're doing, I don't care what you do. That's fine. So, right. So, call that a transformation must be a bijection. What is a bijection?
Functions defined onto.
Yeah, so a transformation is a function from the plane to itself, which is one-to-one and onto. Now, a bijection has a special characteristic, namely that if you have a unique point that maps to any given point, you can reverse that process since it was unique. Okay? This means any transformation can be reversed, or to put in more usually used terms, inverted. That is, we can go backwards from, if we take a transformation, take a point in the plane, operate a transformation on it, you know what point your result came from. So you can go back to that point. Okay? And in fact, so we can define an inverse transformation as follows. So I'm going to define a transformation. I really should say, given a transformation gamma, let's set gamma inverse, which also goes from the plane to itself. I guess I should say define, not set. Define gamma inverse so that if we have gamma of p is equal to q for unique p and q, then gamma inverse of q is equal to p. For all q in the plane. Okay, let's take a second to check with ourselves that this definition makes sense. Remember, gamma is a transformation, so it has to be onto. It has to hit every point in this plane. Q ranges over all points in the plane. Okay? So in other words, that truly is the domain of gamma inverse, if we define it in this way. Okay? And remember, P and Q are both unique. So right away you get that gamma inverse is one-to-one and onto. Okay? Okay. So, jeez, these marks are terrible. So, I've defined the inverse of a transformation. Just as last time I defined what the identity transformation is, I said that a set possessing that has the identity as an inverse has the identity property. So I want a corresponding property to this definition I've made. Okay? So a set of transformations recursive G satisfying if gamma is in G, it implies gamma inverse is in G, is said to have the inverse property. Okay? So here's the important thing here. Any transformation has an inverse, but you might be able to consider a set of transformations such that the set of transformations you're considering contains an element, a transformation, whose inverse is not also in that set. That is to say, this property is non-trivial. There's sets of transformations that satisfy it, and there are sets of transformations that don't. Okay, and we'll see examples. Okay, so additionally, given any transformations, alpha and beta, we can combine them to form a new transformation. Okay, so now I'm going to draw you a schematic diagram. Here's a transformation alpha. And then after applying alpha, we can apply beta. Right? Again, because transformations are one-to-one and onto. Right? So I take all the points of the plane, and by alpha I get all the points of the plane again, permuted in some way, changed around, however alpha does. And then I can take all the points of the plane and move them by beta, transform them by beta. Okay? Well, it turns out I can combine these to get to the same place. How is this? Yeah, this is, remember that at the base level, aside from the definition of, the first component of the definition of a transformation is that it's a function from R2 to R2. That means composition is well defined, right? Okay, so how do I combine these? Beta composed with alpha. Okay, now this is an often confused piece of notation, right? Not the least of which there's a bunch of different types of letters flying around, but the composition of functions happens on paper. You write it down in the reverse order of how it happens, right? First alpha happens, then beta happens. Yet we write it beta composed with alpha. Which when you say in words, kind of makes sense, but written down, this takes a while to internalize.
These functions go outside in.
Yeah. Right, okay, so let me just say, beta composed with alpha alpha and then beta. Okay? The schematic is the best way to remember what's actually going
I'll
on.
keep in parentheses.
Parentheses is fine too. Any way you think of it, as long as you get it right, it's fine. Okay, so caution. In general, beta composed with alpha is not equal to alpha composed with beta. Okay? That is to say, even though the arrows all go in the same direction, it depends, again, the schematic makes it clearer, I think. These are obviously different pictures, right? I've switched the roles of alpha and beta. Okay? That's why I think the pictorial representation of graph composition is the best. Okay? Okay. So, and finally, what's the definition of this symbol? For any point in the plane, we have, well, what I'm saying is this is another mapping from R2 to R2. So it had better operate on the points of the plane, right? I should be able to push a point into that. So beta composed with alpha evaluated at some point is just beta of alpha of p. Okay, that's this is the definition of what this symbol hollow circle means. Okay? Which again is just the same as the familiar concept of composing functions that you've encountered in calculus at least. Okay. So now, we know that beta composed with alpha, sorry, that's a really sloppy one. Beta composed with alpha is a mapping. How do we know it's a transformation?
You can look at how it preserves the vectors.
Well, what do we need to do to show something's a transformation? We have to show that it's both one-to-one and onto. So let's do that together. Okay, so alpha and beta transformations then, beta composed with alpha is also a transformation. Okay. So, I mean, this might seem intuitively obvious, but we should take the time to actually say the steps why it's true. Okay? So, again, we must show beta composed with alpha is onto and 1-to-1. Okay, let's start with onto. Okay, so for any point C in the plane, there is a unique B, of course also in the plane, so that beta of B is equal to C. Since beta is onto, because beta is a transformation, so it has to be 1-to-1 and onto. Okay? And for all points B, there is a unique A, also in the plane, so that alpha of A is equal to B. Again, alpha is onto, since it is a transformation. Okay? So, combining these facts, we can produce a unique A that goes to C via B composed with A. Beta composed with alpha, sorry. Therefore, there is a unique A so that beta composed with alpha, composed of A, which, let me remind you, is just beta of alpha of A, is equal to beta of B is equal to C. Okay, so the composition is on.
Already in fair proof, isn't it? At least the word unique.
Oh, you're right. I really shouldn't have said unique. I mean, that's true.
Yeah.
It's still true. Right. If I were, thank you. That's good. The uniqueness here comes from being 1-to-1 as well as onto, which is still true of both alpha and beta. So really, we're done here. Sorry, I got ahead of myself. But let's do another proof of the fact that it's 1-to-1. Proof. Sorry. I like it when my students pay attention. That's good. So, again. Okay, so let's suppose, remember we had this alternative, this independent characterization of 1-to-1-ness, right? Which is to say, if the image of 2 points are equal under some transformation, then those points must have been the same. So let's suppose that beta composed with alpha of P is equal to beta composed with alpha of Q. And our goal is to show that the points P and Q are actually the same. Okay? So, well, this is obviously equivalent just by the definition of composition to say that beta of alpha of P is equal to beta of alpha of Q. Then, since beta is 1 to 1, we must have, since this equality is the case, we must have alpha of p is equal to alpha of q. Have alpha of p is equal to alpha of q. Then, since alpha is 1 to 1, we have P equals Q. Okay, so again, this is not a hard proof, but it is important because it shows that if you're dealing with nice maps, such as transformations, usually you'll get inherited properties for the composition. Just like we just showed with one-to-oneness and onto-ness.
Important for a group.
Yeah, very important for a group, which we'll say more about now. Okay, so that completes this proof. This is a symbol you see in books a lot. It's just a filled-in square. That means the end of a proof. Okay, just want to delineate things as clearly as possible, so I usually put that on the board. Okay. So, again, we'll go back to describing a set of transformations. A set of transformations G satisfying alpha and beta elements of G implies that beta composed with alpha is an element of G, is said to have the closure property. Okay. Why closure? Well, that just means that there's no way to escape. You can't get out by composition. Right? You're going to remain in G no matter what you compose with if you started in G and you compose with something in G. Okay. Okay. So, the proposition. A non-empty set of transformations again, we use the notation script G. Satisfying the inverse property and the closure property must satisfy the identity property. Okay. So, where does this come from? This is a little bit to assume that my set of transformations is not empty. Which seems kind of like a trivial assumption, right? But it's actually...
If you compose with your inverse, you're going to get identity transformation.
Yeah, that's right. So we haven't spelled that out. So let's go through the steps necessary. We have some comment here. And Spencer also says a transformation composed with its inverse is the identity. That's right. So let's prove this together, and then along the way, we'll see exactly why that is. It makes intuitive sense, right? If you invert something, if you undo something, or reverse it, as we put in quotation marks before, then you end up exactly where you started, right? You start with the transformation, take some point to some other point, and then apply the inverse to that same point, you get back to where you started. Remember, that's where we started today. The identity transformation does not. Okay? Good. So, let's start by taking gamma, an element of G, which we can do because we assumed that script G is non-empty. So it has to have some element in it. Gamma. Since G is non-empty. Okay. So this implies that gamma inverse is an element of G by the inverse property. And we assumed that G has the inverse property. Okay? So by closure, gamma composed with gamma inverse is also an element of G, right? But as we were just saying, gamma composed with gamma inverse of P for some point P in the plane is just equal to gamma of gamma inverse of P. Okay, so assuming gamma maps Q to P, remember that we need that in order to define gamma inverse. Where gamma maps Q to P was used to define gamma inverse. Remember, that was the definition of gamma inverse. We take what gamma does and literally undo it. Okay? So, this is true for all points P. So, gamma composed with gamma inverse for all points P is just equal to P. That implies that gamma composed with gamma inverse is just equal to the identity transformation, because it has the same value on all points. That's what characterizes a transformation, where it takes the points of the plane. So since gamma composed with gamma inverse does exactly the same thing on all points as the identity, these are actually equal. Okay, so now, to be fully rigorous, I have to verify the opposite direction of this. That is to say, what happens when I compose gamma inverse composed with gamma? I'm not going to write that out, but it's the same argument. It's a completely symmetrical argument. completely symmetrically. Gamma inverse composed with gamma is also equal to the identity transformation. So, this implies that the identity transformation was in our set of transformations G. And G has the identity property. Okay. So, those of you familiar with group theory, we're done, right? We defined a set of transformations that is a group. Have an identity, we have a law of composition and closure. We done? I'm seeing a couple head shakes no, and that's the correct answer. That's the reason, that was the answer I was looking for. Not only do we have this notion of composition, which corresponds to our usual notion of function composition, but we also need to verify that this is associative, or insist that if we want to study a group of transformations, that the composition be associative. That is, given three transformations, we can put parentheses anywhere in between them. And that's the same. You get the same result.
The picture seems like it should say that.
Yeah, that's right. Yeah, so it's actually, you end up having to draw pentagons for associativity. but yeah, that's neither here nor there. I wish I could say more, but we'll postpone that conversation to possibly office hours. Okay, so the set of transformations is said to satisfy the associative property if for alpha, beta, and gamma in script G, we have, well, just what you would expect. Gamma composed with beta composed with alpha. And I'll write this in evaluative notation. I'm going to evaluate this at some arbitrary point P. Okay, so this is just, remember the definition, I'm going to use the definition of composition on this open dot. This is gamma of beta composed with alpha of P, which of course is just gamma of beta of alpha of P equal to, well, now I can undo this series of compositions in the opposite fashion. Gamma composed with beta of, what I meant was gamma composed with beta of alpha of P. Right, I've undone these two here. I guess to be consistent, I should put parentheses there. Okay, is equal to gamma composed with beta composed with alpha of P. So the important things are the last two, the first and the last. that this is equal to this. And here I'm just showing you the justification of why this should be true. Okay? I'm just saying that, what am I trying to say?
That for transformations and compositions is probably as trivial.
For the group of all transformations, yes. Right. So again, as we move forward, we'll talk about different subsets G of the set of all transformations that satisfy these various properties or don't. Okay? So, yeah, Zach is right that for the set of all transformations, this obviously holds. If G is the set of all transformations, we've just used the definition of composition to show that that always holds. But when you restrict the subset that you're paying attention to, it may fail, or maybe not. This is actually a homework exercise that we'll do, that I'll assign at the end of next time. Okay? So, good. So this is what I mean when I say we're going to study groups of transformations. We're going to study subsets of the set of all transformations that satisfy all four of the properties that we just introduced. Okay? So, a group of transformations G is a subset of all transformations satisfying the identity, what order did I write these in? Inverse, closure, and associative. Properties. Okay? In fact, this is a version of the general definition of group. So in fact, any set, not just a subset of a group of transformations, but any set, let's call it capital S, satisfying these four properties is a group. And group theory is a very profound and difficult, long-standing branch of mathematics. Okay? But again, just to bring this back, this is the purpose of this course, is to get grounding in this difficult theoretical subject with the concrete examples of groups of transformation. Groups of transformations. Okay? So, right. So at the end of tomorrow, or perhaps the beginning of Thursday, I'll say a little bit about general groups. Talk more about what you actually do when you do group theory in general. But not too much. Okay. So, here's a theorem. And, well, let me write this down. So the set of all transformations is a group. And not only that, but obviously a transformation group, right? Because it is comprised of a set of transformations.
In composition.
Under composition, yeah. So right. That is the subtlety here when I said any set satisfying these properties. We only define closure in terms of composition. An arbitrary group might have a much different way of combining two elements such that you get a new element also in the set S. But unless otherwise stated, we're always assuming the way of combining elements is composition. Okay? So I'll just put that in parentheses. Under composition. We've essentially already done this. Okay? This is what Zach was alluding to when he said, well, what we've shown here is that this associative law holds for the set of all transformations. Okay? Now here's the second part of this theorem. The set of all collineations is a transformation group. Again, under composition. And in case this is confusing, when I say is a group, I just mean transformation group. Right? Just because this is a set of transformations. Okay? Okay, so here's your homework for tonight. Show the set of all collineations is a group. Okay? Now if you look carefully at the notes from today, you'll see that in reality we have done a lot of work toward this already. It's not as daunting a task as you might think. But yeah, we'll discuss that first thing tomorrow. Let me just say a few more things, and then we can adjourn. Okay, here's a definition. And every element of a transformation group let's call it G2 is also an element of a transformation group G1. We say of G1. Oh, sorry, Anirudh asks, are those two separate theorems? It's two statements that I combined to the same theorem. Technically, you could state them differently. You could split them apart into two theorems, but matter of taste. I'm only asking you to prove that the set of all collineations is a group. The second part of this theorem, or the second theorem if you like to split them apart. Either way. Okay? Okay, so this is everybody's familiar with the subset relation, right? If you take a set of things and you take any number of those things from that set, you form a subset. Not so with subgroups, right? Let's take this sentence one of this theorem for granted and say that we're totally convinced that the set of all transformations forms a group. Can anyone tell me a subset of the set of the group of all transformations that is not a subgroup? Yes?
The empty set.
The empty set, yeah, good. The empty set. Why is the empty set not a subgroup?
It doesn't have an identity element.
It does not satisfy the identity property. It doesn't have an identity element. Okay, so note. A subset is not necessarily a subgroup. E.g., the empty set is a subset of the set of all transformations. But is not a group, since there's no identity, since it doesn't contain, the identity transformation. How do we know it doesn't contain the identity transformation?
It's not.
The empty set has no elements, right? Okay, so yeah. There's a lot more examples here. In fact, why don't I just say, here's
Too easier to take out exactly one.
yep, that's the way to go too. Why don't I just say, homework. Do this tonight too. This will be easy. Let G be the set of all transformations. Construct 3 examples of subsets of G, which are not subgroups. Oh, I guess really I should say here, the group. Okay? So, on that note, I think we should adjourn for the day. And tomorrow we'll talk about special types of transformations, involutions. These are elements in our groups of transformations that possess special properties that will help us characterize groups of transformations. Okay? Any questions before we go? Well, I'll take that as a note, but again, email me anytime.
Bye. Thank you, Professor.